Okay, here we go with a quick run back through potential dividers. Now, this is NAT 5 revision, so this is something that we should have an idea about. It really is just our basic voltage rules, that the voltage across this R1 and the voltage across R2 will have to add up to our supply voltage, whatever our supply voltage is. So when the circuit is rotated, you've still got the same thing. You've got a supply voltage here. We often say, if we're going to name resistor R1, that will probably have voltage 1, and resistor 2 will have voltage 2. And it doesn't really matter which way around you do it, as long as you're consistent. And another way to change this, so we're going from the basic circuit rule, this voltage will be the sum of these two voltages. We can rotate the circuit onto one side, and then when we replace it with this other way of writing out a direct current power supply in this way, then of course the voltages will still add up. So V1 and V2 will both have to add up to this 5 volt that we've got in this situation. And I've neglected to draw the circles all the way down this page because I kind of thought I'd not do a very good job of it, perhaps. So let's move on. So we've discussed that. Now that rotates to become that, and this is a series circuit, so the current is the same for both resistors. And if you start looking at that then, so let's try and do it in steps. So let's just say, if V1, if I can work out the current in the circuit and say, okay, I know the current I, then the voltage across resistor 2 will be the I times resistor 2. And the voltage across resistor 1, as I've drawn it in this case, will be the I that we work out multiplied by resistance 1. So that's quite straightforward. But if you then start thinking, well, hold on a second, what can I do with these two? If you say this is a V, this is V2. So if you do the ratio of the two, V1 divided by V2, well, if I take the equation for each one, R1 times I and R2 times I, if I was to, that kind of cancels. So V1 over V2 equals R1 over R2 because the I's are on top of each other. It's a little bit untidy there. But this is an important result because you can use that if you want to as part of your problem solving routines, and that does appear on the equation sheet. So we've got that as a general trend, okay? So, and that establishes this key point that the largest resistance will have the largest voltage. So let's try working out V1 and V2 for a certain particular system. So for this system, I've decided to call the top one V1 there, and the bottom one V2. 6 volts. Now, at NAT 5, we often use this equation, which is one of the particular voltage will equal the supply voltage times by that resistance divided by the total resistance. And so that's pretty straightforward. Here I've got 8. V1 will equal the supply voltage of 6 times by 8 R1, 8 ohms, divided by the sum of the two resistances, 20 ohms. And I get V1 is 2.4 volts. Now, if I'm super confident I've got that right, I can then say, okay, well, if there's 2.4 volts there, then there must be, to get up to 6, these two have to add to 6. To get to 6, then 2.4 plus 3.6 will get me to 6. So I can work out that V2 is 6. And what I haven't suggested to you is that V2 clearly there is actually 6 minus 2.4. That would be my working out. Okay, so I must have talked for long enough, so I'll shut up and say, why don't you pause the video and do those? Just move that across a little bit. Okay, you pause your video. You're on sheet D. Have a go at working out V1 and V2 for all those. And of course, I do mean I want you to work out this voltage. I want you to work out, let's call that V1, V2, V1, V2, V1, V2, and then this V2 here, and there's a V2, that's a V2, and you can see I've done something clever there. So, and you should probably work out the V1 there as well. Okay, you have got that, and we'll discuss your answers in person. Okay, moving on, I forgot to mention earlier that you could also have a play at doing, if you don't want to bother learning the other equation, which shows extreme laziness, you could do, you could say, oh, I can't bother doing that. Why not just have a go at doing Ohm's law twice? So here's an example, 12 volts, 4 ohms, 6 ohms. Just use V equals IR twice. The first one will be to find the current. So if I use the supply voltage, that should be V. Supply voltage will equal the current times the total resistance. So my supply voltage of 12, my current is unknown at this point, and my total resistance is 6 add 4, 10 ohms. So I bring my 10 across to get I equals 1.2 amperes, and then to find V1, I go back round my Ohm's law equation, and for V1, I'll be using R1 and the same current. Now, it's important here that I can consider Ohm's law just for one resistor, or I can consider it for the whole circuit. And it's important that you get the resistance of the whole circuit, or just the one resistor. So, because I'm just doing one resistance, I just need that resistance. Remember, it is a series circuit, so the current is the same. So you've got to pick the right resistance to get the right voltage, but the current will be the same. Okay. One thing that I didn't discuss in detail in going through it is what happens when things change. So if I go back through the same example that we had in sheet E, and change the resistance, then, so here, let's go through this one. I've decided to go from 4 ohms, 6 ohms to 4 ohms, 3 ohms. So what do we know? We've now got less resistance in the circuit. Total resistance has decreased from 10 ohms to 7 ohms. So current will be increased. The voltage supply hasn't changed, so if we have less resistance, we will get more current. And R1 is now greater than R2, so it's the greater resistance, so it will have the greater voltage across it. If you remember previously, in the previous example, R2 was the greater resistance, and so R2 had a voltage of 7.2 volts across it, and R1 had a voltage of 4.8 volts across it. So let's see where we end up. So I like using this one, even though it's not on the equation sheet, so you have to remember it. And so I've done, to find V1, 4 over my new combined resistance of 7 times by my supply voltage, and I get 6.9 volts. So that V1 has gone up from 4.8 volts to 6.9 volts because we've changed this resistance. And now the resistance here has gone down. It was 7.2 last time, and now it's only 5.1 volts. Okay, but how are you going to achieve a reduction in resistance like that? Well, the most obvious way is to put a resistor alongside in parallel. So you have a go at this little example. In the first part of the question, you've got a 10 and a 5. In the second part of the question, the 10 now has another 10 alongside, and you have to consider them together to get V1. You have a go through that one, and then we can discuss it together. And there's another one for you to have a go at on page H. Okay, I'll bring that to a close there, and we can look at moving on to our particles revision in the next video.